everyone, it's Mr. Oakes. So we're going to talk about how to identify irrational numbers and really what that means. Basically, what an irrational number is a number that cannot be written as a ratio, or simply put, we can't write it as a fraction. So I have here basically a chart that represents all the real numbers. So we notice in here, it's a little crowded in here, but the real numbers contains all these different things. I'm going to look first at this group up here. It's called the rational numbers. And what you kind of see is that it's this big box right here. And rational numbers are the numbers that are actually like fractions, terminating decimals, and repeating decimals. So some of the examples I have are -4/5, 0.75, which is a terminating decimal. This says 31.8. It's a little tough to see. That's 31.8. Again, a terminating decimal. And here I have 7.54 repeating. So that's something where it's a repeating decimal, and I can actually rewrite these three numbers as fractions, and this one already is a fraction. So that's why they're called rational numbers. And then we kind of get a little smaller. I always think of the real numbers as it's a big box that has a bunch of smaller boxes within it. So the next biggest box is rational numbers, and within rational numbers there's another box called the integers. Now the integers really are, we don't have any fractions, we don't have any decimals, but we do have negative numbers, and then everything, all the positive numbers that go along with it. So things like I have a -5. This says -16/4, and you'll be like, but Mr. Oakes, you just said we can't have fractions. Well, don't forget, a fraction is the division problem. So I have -16/4, and 16/4 is 4, so I have -4. So that's okay. Sometimes they're in disguise. And lastly, I have -1000. So those are three negative numbers that are specifically, I can say those are integers. But everything that I'm going to keep going in can also be included in integers because it's another box. The next smallest box is called the whole numbers. And there's only one special number that is particular to whole numbers, and that's 0. So basically whole numbers are all the positive numbers including 0. And if you stop and think about it, when you look at a 0, it looks like a whole, so it's a whole number. Lastly, we have what are known as the natural or counting numbers, which are basically the first numbers you learn. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc., etc. So I have here as examples 19, which is definitely a counting number. I can count to 19. And square root of 4, which again, we're like, but that doesn't look right. Square root of 4 is a perfect square. 4 is a perfect square. And when I take the square root of 4, really what I'm saying is what number times itself gives me 4? Well, that's 2. 2 times 2 gives me 4. So that's really what square root of 4 is. It's 2, and 2 is a counting number. But then I have this box down here that's not within this big rational number box. It's called irrational numbers. And those are the ones we're going to focus on. Irrational numbers cannot be written as a fraction. So if I try to put them in the calculator and do fraction to decimal, it's not going to allow it. Alright? So things like square root of 2. Well, square root of 2 isn't a perfect square. There's no number that times itself gives me 2. Alright? A lot of you are probably right now going, well, what about 1? No, 1 times 1 is 1. 1 plus 1 is 2. But we're not talking about addition, we're talking about multiplication. So this is irrational because if I tried to figure out what number times itself gives me 2, there's nothing there's nothing nice. We'll get a decimal that doesn't come out nice. This little symbol here, pi. Pi is the most famous of the irrational numbers. 3.1415, etc., etc. It just keeps going. There's no repeated pattern. It doesn't end. There's no terminating thing. I can't write it as a fraction. I can write a fractional approximation, but really there's no fraction that works perfectly for pi. Negative square root of 3, again, 3 is not a perfect square, and the fact that it's negative doesn't really matter. It's the fact that I don't know of any number times itself that gives me 3. And then I have down here 1.12, 112, 1112, etc., etc. And at first you might be like, Mr. Oakes, but that's repeating. It's got a pattern. Yes, there's a pattern, but the pattern isn't a consistent pattern that stays the exact same thing over and over. All right. So this, because each time we're adding another 1. All right. So 1, 2, 1, 1, 2, 1, 1, 1, 2. The next one will be 1, 1, 1, 1, 1. I'm losing track of it. But it's not the same thing every time. Okay? So that's why this is irrational, because the pattern technically changes every single time. It's not repeating itself. So with that, we'll look at a couple of questions. The first question I have here, and it might be a little bit difficult to read, but I have is 5.78778778 ... a rational or irrational number. Well, if you remember our last example, the 1.121121, the pattern kept changing. So even though there was a pattern, and it was every single time after a 2 I add another 1 to it, it's not repeating that true pattern of the same 2 numbers over and over, the same number or the same 3 numbers, or etc., etc. So this is irrational. All right, this is an irrational number because the pattern is not consistent. It's not staying the same all the time. Okay? Here is square root of 42 rational or irrational? Well, if we stop and think about it, we can think about certain numbers that are perfect squares. So something like 36. 36, the square root of 36 is 6, because 6 times 6 gives me 36. Well, I could do 7. 7 squared, so 7 times 7 gives us 49. Okay, so the square root of 49 is 7. Well, 42 falls in between those two. There's nothing nice that we multiply together to get 42. So square root of 42 is irrational. If I tried to put it in my calculator, the decimal would be somewhere between 6 and 7, and there wouldn't be any true pattern that I could say, oh, that's repeating pattern. Okay? Circle the irrational number below. So I'm going to look. The first one I have here is 7.27 repeating. Because the decimal is repeating, I could write that as a fraction, and we've done that lesson. Okay, so I have a repeating decimal. That's rational. Five over 9. It's a fraction. It's a ratio. So therefore, rational. Square root of 15. Well, if I go 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16. So square root of 15 falls in between the square root of 9 and the square root of 16. So there's no good number that I can multiply by itself to give me 15. So that's my irrational number. This last number, square root of 196, that's 14. So just because I have a square root symbol there doesn't automatically make the number irrational. Because if I can take the square root, then it's not irrational. Lastly, I have this one here. Dina says 73.56238 is irrational because it doesn't repeat. Do you agree? Well, remember that when we're talking about decimals, a number is rational if the decimal repeats or it terminates. And terminate is just a fancy word for it ends. I don't see any ... after this. So that tells me that this number ends. So Dina is incorrect. This is a rational number because it has a terminating decimal. And that's it. That's how I know that that's a rational number. Does it have a decimal? If so, does that decimal terminate? Yes, it's rational. Does the decimal repeat? Yes, it's rational. Can I write it as a fraction? Yes, it's rational. If I can't answer yes to any of those questions, it's probably an irrational number. Irrational. Okay? Cracker. So that's it. I hope this video is helpful, and I'll see you guys soon. Bye bye.